Hello, class. Okay, so we're going to do a rotational dynamics lab where I've got three objects here, a disc, a ring, and a rectangle. And we know how to calculate the moment of inertia of each of these objects just based on geometry, the masses and dimensions of the objects. But I also want to experimentally measure these. So what I have, we have this device here. Let me hold this up for a moment. You can see on the bottom of this is a platter with a spindle. So this is a spindle. And what I've done is I've wrapped a string around this lower one here. There's three different radii. Let's see, three different radii. So I wrapped this string around the smallest one. And it's very important to know which spindle you're on and what the radius of that is. And so this is a very common source of confusion because we want the radius of the spindle, and this platter also has a radius, and students often use the radius of the platter, but we want to make sure to use the spindle radius. So the idea is we've got the string, so if I, like right now, this spindle's at rest, kind of hard to see, but if I pull the string, it's spinning now, it's accelerating. And I want to make sure I rewrap this properly so it, okay. And so what we're going to do, by pulling on the string, I'm exerting a torque, and that will exert, and I'm going to make this string more horizontal here. So if I pull on this, I'm exerting a torque, which is causing an angular acceleration. So what we're going to do in the experiment is hang a fixed mass to the end of this string and then release it. And so I'm going to have to go to the board. So I'm going to move the perspective here a little bit. So let's see if we can see the board. Yeah, good enough. So basically what we have is, this is the string wrapped around the spindle, there's a hanging mass, that's the platter. And let's look at the mass. Let's say downward is our positive direction here. There's gravity downwards. Now I'm not going to do this entire thing for you, but I'll just get it started. So applying Newton's second law to this mass, it's going to accelerate downwards. So we have mg minus t equals ma. Now, how do we actually measure the acceleration? I should have talked about this first. Here, this is the pulley here, and it's hooked up to a photo gate. So you can see when the spokes, as it's rotating, the spokes are going to be constantly blocking the laser beam, and the more quickly you rotate it, the more often that's going to happen. And so this, it's called a smart pulley. It can measure the angular acceleration. So that's what we're actually going to be measuring here, is the angular acceleration of the rotation of this pulley. And that's related to the linear acceleration by A equals R alpha. Okay, so we can measure the acceleration of this falling mass using the smart pulley. The computer knows all the details, like the spacing between the spokes, like the angular spacing and the radius and all that it needs. So we have one equation here. And mg, that's Newton's second law applied to the falling mass. Now the torque on the spindle is the tension times the radius. And again, if we look at it from a different perspective, like here's the platter, the string is wrapped around this spindle. So we have a tension here, and it's at a radius r, so the torque is the tension in the string times the radius of the spindle. Now again, because you're not actually doing the lab, oh no, you actually will have both radii for the spindle and the whole overall platter. So yeah, you want to make sure that you use the right one. Okay, and so for that we can use torque equals I alpha. So we have T times R equals I times alpha. And you want to use the information that you are given to find the moment of inertia of this rotating platter. That is the goal. And let me go back to the experimental setup. See if we can get this positioned right so you can see it. So really, I mentioned earlier, we have these objects, like say this rectangle. So I tried to get this to balance where I want it. Hopefully it stays there. So let's say we want the moment of inertia of this rectangle. What we're going to do is put the rectangle on the platter and then do the experiment. And so what we're getting here, so using those equations, we can solve for the moment of inertia. And then we can measure it using this setup. But what we're measuring is a moment of inertia of this combination of the platter plus this object on top of it. And so we need to know the moment of inertia of this platter with the spindle on it. And so we're going to use this setup to do that. So the first trial, the first part of the experiment, the goal is to measure the moment of inertia. Sorry, I've got to move the camera. Okay, so the first thing we're going to do is we're going to run this experiment with just the platter itself 3 times and measure the moment of inertia each time, and then we're going to take the average of that, and that will be the moment of inertia. I'll call it PS. That's for the platter with the spindle. So again, you just hang a mass, let it go, let the smart pulley do its thing, and yeah, with a combination of these equations, basically you solve for I, the moment of inertia. And so, yeah, I don't want to give away all the details. So I think what we'll do is we'll talk about this in class, or there will be a time to ask questions about this during class. You can't figure out the moment of inertia, like how to get that. But just say you figure that out. So you have the moment of inertia. You have to do the experiment to get the acceleration of the falling mass, and then you plug that in and you get the moment of inertia. And we do that 3 times to get the moment of inertia of the platter plus the spindle. And then let's say we place the rectangle on it and do the experiment again. So now we have this rectangle on top of it. And so if we do this experiment, so ultimately from here, we're going to have I equals something, where we just plug in the acceleration of the falling mass, and we can then just get the moment of inertia. So what we're measuring, this is part A, getting this, part A. And then part B, we're going to place an object on top of it. So here we have platter with a spindle. Let's just call this object O for object. And so we do the experiment, we get the acceleration of this falling mass, plug it into this formula, and what we're measuring is the total moment of inertia of whatever's spinning, which is, so what we're getting is I, platter, and spindle, plus the moment of inertia of that object. So in part B, that's what we're measuring. The platter and spindle, plus the object that we're actually trying to find. And there's no way around that, really. It's kind of like, imagine if we designed a scale where you put a mass on it, and it gives you a reading. And, but what if you couldn't fit your mass on, so you had to put a bowl on top of the scale, and then put the mass that you're trying to measure inside the bowl? you're measuring the total mass, the bowl plus the object. Now in a normal scale, you could just put the bowl on top of it and then zero it. So you just record what you're trying to directly. But say you couldn't do that. You know you're measuring the mass of the bowl plus the object. So if you want the mass of the object, you just subtract the mass of the bowl. So that's what we're doing here. We get the total moment of inertia of this combination. So the moment of inertia of object O could be the ring, or the rectangle, or the cylinder. We take whatever we measure and plug into this formula, and then we subtract the result from part A. So part A, the point is to find the moment of inertia of that rotating platter just so we can subtract it later. And so we're going to do that for all three objects, and then we're going to compare to the theoretical values, which we get from measuring the geometry of the situation. Like for the rectangle, we measure its length, its width, and its mass. And there's a formula, and so we should, just plug those in and compare the results then. So we're using our formula and our experimental setup, and then we compare the two results. So that's the idea behind this moment of inertia. Way to measure these moments of inertia experimentally. Okay, so yeah, that's all we're doing in this lab, so that'll be it for that.